Hello everyone, welcome back to the latest lecture session. A quick recap of what we have been up to in the last session, or rather than recap, we will just look at what are the take home messages. We looked at different ideal case reactors, batch reactor, CSTR and plug flow reactor. We looked at how or why they are needed for us in water and wastewater treatment, or when we are trying to understand water and wastewater treatment, right? And then we looked at applying mass balance equation for the batch reactor, the plug flow and the CSTR. We also looked at the fundamental mass balance equation, which I just threw into the mix to help you understand that there is a more complex system at hand, but we typically simplify it to use it or apply it to the ideal case reactors now, right? And then we looked at comparing CSTR and plug flow reactor, and we saw that for the same volume and for the same flow rate, we saw that plug flow reactor typically is more efficient than a CSTR. Why is that? We saw that the rate throughout this CSTR has to be relatively low because the outlet concentration is typically low. That is what we want, right? And that is not the case in the plug flow reactor. Why is that? Because in a plug flow reactor, the concentration changes with distance and is not the same as the concentration in the outlet. So, let us move on and see what else it is that I have out here. So, we have conservative systems, no reactions, as in until now we looked at non-conservative systems, right. I should have probably discussed this easier aspect first and come to non-conservative systems, but pardon me, first discuss the conservative and then come to non-conservative. But I always like to get the difficult part out first because people typically overthink things. So, non-conservative, we are done with that, right, but let us look at the case when we have no reactions. For example, this is my river coming in or canal, and this is my wastewater coming in from an industry. So, Q from the wastewater and Q of the canal, and let us say this I am going to call as the Q river, let us see, and the concentration or the BOD here is, let us say, C waste, and here it is C of the canal and C of the river. So, if I know these four variables, how do I get this particular concentration of the or the BOD levels in the mixed stream, which is the river, and keep in mind that the flow is going in this direction. How do I get that? Again, mass balance, let us say here we are assuming steady state. So, what is the fundamental mass balance equation? We have the accumulation term is equal to Qn minus Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss. But here we are assuming, or we are saying that it is a conservative system. So, this term is 0, and if it is at steady state, this term is also 0. So, what is it that I have? Qn Cn mass coming in is equal to the mass going out, right. So, that is just it. Qn Cn is equal to Q out C out. So, if the mass balance is over, let us say, this particular control volume. So, mass coming in is due to two streams, Q of the waste into concentration of the waste plus Q of the canal, and concentration of the waste or the compound already existing in the canal is equal to the mass going out of the system. And how is the mass leaving the system? Here, this is what we have out here, right. That is the in the form of the river, flow rate of the river into concentration or the BOD in the river, let us say, right. So, that is what we have. But how do I get this? So, it seems like I have only one equation and two unknowns here, but how do I get it? So, here I can also apply it over the mass itself, let us say, and not assuming. So, Q waste into density of water plus Q canal into density of water is equal to Q river into density of water. So, assuming that the density of water is the same, here what is it that I end up with? QW plus QC is equal to QR. Obviously, we can write it or understand that without looking at this equation 2. The waste stream is coming in and canal is coming in, and both are joining to form the river, let us say. So, that is what we have, Q waste plus QC equal to Q river. So, from that we have Q river, and so we just need to find C of the river, concentration of the compound in the river, and with one particular equation we can solve for this unknown, right. So, conservative systems. So, in this way different aspects can be looked at. Here we are just looking at two streams joining. There are other examples which might be slightly trickier and which we will try to apply out here, right. So, let us move on to the other aspects I wanted to look at. So, when we are talking about CSTR and plug flow reactor, we always talked about them or referred to them as ideal systems, right. As in we are assuming complete mixing within our particular CSTR, right. And let us say if I want to understand how a lake behaves, we typically apply the CSTR model to the lake. But in a lake, let us say the inlet is at one end and outlet is at the other end. Do we really presume, or can we presume that the lake is completely mixed? No, right. It does not really, that is not how it works out there, but these are the assumptions we are making. But you can look at different aspects as in short circuiting and such when we look at the non-ideal systems, but we are not going to go into that in that detail, especially because this is an undergraduate course, right. But we will just look at understanding some of the real systems. Yes. So, one case is having a series of CSTRs, and what do we have out here? We have flow coming in, flow going out, and complete mixing. But if it is a series of reactors, what is it that we have? This outlet will be the inlet for the next one, and so on and so forth. We have that in series. Then what is it, or how do you think that will behave? Let us see. So, in general we should not have let the cat out of the bag. So, if n is equal to 1, number of reactors is 1, obviously it is a CSTR, it behaves as a CSTR. But if it is n equal to infinity, let us say, right, it will end up behaving as a plug flow. We will briefly look at that particular data or set, let us say, right, or information. And if n is greater than 1, it is finite, it will behave like a real reactor. Again, in the context of our particular wastewater treatment, I am not talking about it in terms of the lake, right. If I am talking about the lake and if this is the flow coming in and this is my lake, it is not as if everything will be mixed, some water will go out here, some will be short circuited and directly come out here, right, and you have the depth of the reactor also playing, depth of your lake also playing a role, and so on and so forth. But we are not going to look at the natural systems, we are looking at the engineered systems here, right. So, if n greater than 1, it is a finite or real reactor. So, when we applied the particular mass balance equation to a CSTR at steady state, and rate of formation is equal to 0 and rate of loss is based on a first order loss reaction, we see that it was Kc. What is it that we ended up with? I think we had C out or C theta by Cn was equal to 1 by 1 plus K theta, right. Or let me slightly rewrite it so that I can use it here for my case. So, I will write it as C1 is the out and Cn is the C naught, let us see, right. And taking this term out here, what is it going to be? It is equal to this into C naught, right. C out, which is what I am calling as C1, is going to be 1 by 1 plus K theta into C naught. So, that is fine when I have just one reactor out here, right. Let me just change the ink color so that we can, so if that is fine if I have just the single reactor. But let us say if it is two reactors now, how do I go about it? This is the case when n equal to 1, but if n equal to 2, for the first one fine, this is the case, but what is it for C2 here, right, for the reactor number 2, this is for 1. So, C0, C1, pardon me, I think I messed up something out here. Okay, we have this flow going in, and let us say this is C1 and this will be C2. So, what is C2 going to be equal to? C2 is equal to, so if this is theta 1, 1 by 1 plus K theta 2, assuming that the volume is different for the second one, C1. This is the case, right. But what is C1? We know that C1 is equal to this. So, C2, which is nothing but the outlet from my whole 2 CSTR in series system, is equal to 1 by 1 plus k theta 1. Again guys, you do not need to mug anything up here. Typically our exams, I am going to give the relevant formulas and you are going to be able to solve it. You just need to display that you have an understanding of the relevant system into C naught, let us see, right. So, that is what we have, C2 is equal to this when n equal to 2, and if theta 1 is equal to theta 2 and so on and so forth, let us see, right. I should move on to looking at this particular case. So, if theta 1 is equal to theta 2 and so on and so forth, and if I try to generalize it, what will it become? Let us say for C2 it is going to be equal to 1 by 1 plus k into theta I, theta is the one for each reaction, equal to square times C naught. So, similarly Cn, if there are n reactors, equal to 1 by 1 plus k times theta I to the power of n C naught, or what is coming in, let us say. So, this is for the case when CSTRs are in series, yes. So, again no need to mug anything up, but just trying to understand the system. So, let us try to look at some data that we have out here. And you have the reference given here. So, here what it is that people do, they had a lake out here, right, and feed rate is given out here and they injected a tracer. Keep in mind that it is not as if there is a continuous flow of the tracer. Water is flowing into the lake, water is flowing out of the lake or your system, and while the water is flowing in, at one time, at one point some tracer was injected. It is not a continuous injection, just what one event injection of the tracer. So, if it was an ideal system perfectly mixed, what should happen? Immediately everything should be diluted. So, let me understand the graph here so that we can go through the relevant data. On the x axis we have the time in days, right. So, they started at on 7th March at around what is it, 12 noon, right, 12 noon, and then we have the concentration of the outlet here, concentration of the tracer in the outlet, and that is on the y axis. So, if it is a completely mixed system, ideal system, what should happen? As soon as I put the tracer in, it should be immediately diluted, right, and that should be shown up immediately in my outlet. So, that is why we have this theoretical profile of an perfectly mixed or ideal CSTR, let us see, right. But what happens? It takes time, right, and that is what you see. Even though the tracer is put in at this point, it takes some time for the concentration to be become relatively uniform, and then you see the decrease in concentration out here, right, as the water is removing the tracer, or the tracer in the water is flowing out along with the water, right. So, that is what we see, or we see that it is never really ideal reactor or ideal system, let us see. So, that is one case. This is for one system now. And for a tracer injection, and I believe for this particular model they looked at k is equal to 0, right. Again you can look at the reference in detail if you want to. We had the earlier case, right, something like this, but I think it is without the steady state assumption. So, anyhow we have it that if n is equal to 1, right, again dimensionless time here and dimensionless concentration C by C naught. What is it going to behave like? With rate constant equal to 0, this is what it is going to behave like, the CSTR. When n is equal to 1, this is the CSTR. I believe we already had the graph or data for this in the earlier session when we had some rate constant at that time, but never mind. This is the case when we are injecting a tracer again, right. If you are injecting a tracer for a single reactor, this is what it has to look like, right, and that is what we see. But if n equal to 2, you see that the profile changes, n equal to 5 slightly, n equal to 20, I mean 10, 20 and 40, and n equal to infinity, what does it look like? Whatever I put in out here, it just flows out like that. Again this is for a tracer input, I guess, and that is what you see when n equal to infinity, it looks like a plug flow reactor, and that is what we discussed out here. When n equal to infinity, it more or less this system is like a plug flow reactor. When n equal to 1 CSTR, anything in between, it looks like a finite or real reactor, right. So, that is something to understand. Let us move on. And non-ideal systems, plug flow with dispersion, let us say, as in What is the fundamental mass balance equation? We know that it was dC by dt plus del product of flux. What is flux? Mass per area per time, right? How much mass is coming in through a particular area per time, let us say, is equal to plus or minus sources or sinks. Del product means I want to understand what or how is my variable changing with x, y and z, right. So, when we applied it to our ideal case systems and assuming advection only in one direction and assuming that there was no diffusion, we ended up with an equation like dC by dt plus assuming that velocity is the same in compressible liquid, right, u and concentration is changing only in one direction, or the river or the canal is flowing in only one direction. So, concentration does not change with y and z, but only changes with x, and assuming that there is no flux due to dispersion or such, it is equal to plus or minus sources or sinks, meaning rate of formation minus rate of loss. But if there was diffusion, what is it that it would have been? It would have been, I guess, flux due to diffusion equal to minus d, or let us say I should not have written the derivative. Okay, let us go with this derivative dC by dx. It would have been d is the diffusion coefficient or the dispersion coefficient or the turbulent diffusion coefficient, right, second derivative, right. So, when we assumed ideal case, we assume that this does not occur, but think about it in a river. So, whatever I put in here will not just stay like this, right. It is going to mix slightly this way and that way with the preceding and succeeding parcels. So, there will be dispersion, right, because of the turbulence in that particular fluid, let us see. So, if we take this into account, and you can solve this not relatively easily, but people have solved it. So, if you solve this, you will get the case for plug flow with dispersion, right. And let us see what we have out here. Some mixing, meaning with flux is equal to minus d dC by dx, apply mass balance to differential element, and here it is again the reference out here, right. And here let us see what we have. We have input to your reactor, pulse input, meaning one time injection of your particular tracer or pulse, let us say tracer, pardon me, and this is the solution. Let us not go into that, but let us just look at what we have out here. There is a particular variable called the Peclet number, and what is it given as? QL by A into D. D is the not the diameter or such, it is the dispersion coefficient. So, if you look at the numerator and denominator, the numerator will give you an idea about advection, mass flux or mass transport due to advection, and the one at the bottom will be the one due to dispersion, right, or that is equal to velocity UL by D. So, advection by dispersion. Why is that? We will just look at it. So, if P is equal to infinity, what does that mean? Meaning advection or Peclet number, if it is equal to infinity, what does that mean? This numerator is much greater than the denominator out there, right. So, advection predominates and not really dispersion. But if we keep decreasing it and then PE goes to 0, when PE goes to 0, what does that mean? There is no advection, but only dispersion. So, when PE equal to infinity, it is a plug flow reactor, and as we decrease it and PE ends up being 0, it is a CSTR, right. So, that is what we see out here, right, and where it is that your system lies will depend obviously upon this particular Peclet number or such. So, if its earlier case was when I injected the tracer just once, let us say, right, tracer injection, but if there is continuous flow coming in, like my wastewater treatment plant, I have continuous waste coming in. So, how do I solve that previous equation? So, people have solved it for the continuous mass flow, and this is what we have. Again, P is the Peclet number, and A here, which is presented here, this is what we have out here, right. So, for this again let us see what the plot looks like. So, dispersed flow reactor performance for K equal to 0.5 day inverse. So, if Peclet number is high, what will it look like? Plug flow reactor. So, that is what we have out here. As we keep decreasing the Peclet number, what did we say? It was more or less advection. What is advection now? By dispersion. We are not talking about diffusion itself. So, if a canal is transporting, let us say, some contaminants, so you have a net fluid flow in one direction, and thus you have advection there, mass transport due to advection. Let us say diffusion. I think the example that I looked at was, I just opened the scent bottle. Even though right now there is this scent compound, the compound in this scent bottle is only present in this vicinity and not at the end of the rooms or the corner of this room, over some time it will end up there. You know, why is that? Concentration gradient, the system wants to achieve uniform chemical potential. So, you are going to have transport molecular diffusion from here to the different corners of the room, but that is a very slow process. But if I turn on the fans, I have turbulence and dispersion will take place, and it is relatively faster, right. Think of it, fans being turned on or mixing being allowed. There is no advection, there is no net fluid flow in any single direction, but you have mixing conditions. So, you will have dispersion out here. So, advection by dispersion. So, advection, when Peclet number is infinity, that means advection is very high, that is what we mean when we have plug flow reactor. And as we decrease it, that means that, you know, dispersion also has a role, and when it is only dispersion, right, there is no advection, as in this is what we have. Is there any advection here? No, it is completely mixed. So, that is why we end up with this. So, if you remember some of our systems that we looked at earlier, I drew this for k equal to 0.52, right, and we also see that plug flow reactor performance is better compared to the CSTR, right. So, that is what we see out here. And if I take the logarithmic scale on the y axis, I guess this is what it looks like, more or less the same information presented in a different manner out here. So, real systems, they will be somewhere out here. They will not be typically plug flow reactors, they will not be CSTRs, but they will be somewhere in between. That is something for you to understand. But typically in wastewater treatment plants, depending on how you design it, you people might assume CSTR or plug flow reactor, but you need to understand that the actual performance, the deviation will be due to this case, let us see, right. And here is one case where they tried to achieve plug flow reactor system. Let us just try to understand this. What do we have here? We have primary settling tanks in the foreground, primary settling tanks, as in I am just trying to remove the suspended solids which are heavier, right. By gravity they will settle to the bottom, right, they will settle to the bottom. And then there are organic compounds which I will try to remove by the microbes, using the microbes, right. Microbes, though similar to us or me, they need oxygen, which is an electron acceptor, to be able to let the redox process go through. So, that is why I am going to pump in air, that is why you see this particular turbulence. But did they design it as CSTR? Not really. So, how did they design it? They designed it as if the flow was going in this direction and again this direction, like a semi plug flow, or they were trying to achieve plug flow reactor conditions, right. So, that is what you see, it is neither a CSTR nor certainly a completely a plug flow reactor, but they were trying to achieve plug flow reactor like conditions. And then we have the secondary settling tank and such, let us not go there, but I just wanted to show a case where it is certainly not CSTR, but trying to achieve plug flow reactor conditions, right. So, let us move on. So, lastly we will compare the tanks in series compared to dispersed flow reactor, let us see, right. So, this is for the case, I guess, when rate constant is 0 and for only one time injection of the tracer. So, dispersed flow and tanks in series. So, when n is equal to infinity, what do we see? It looks like a plug flow reactor, and when n equal to 1 tanks in series, it is only a CSTR. But with dispersed flow too, we looked at it, Peclet number is infinity, meaning advection outweighs dispersion, then we see that it behaves as a plug flow reactor. When Peclet number comes down and down such that, you know, there is no advection and only dispersion, what is it that you see? It acts as a fully mixed tank. So, from both ways or viewpoints, you can understand the particular system, right. Enough of that, right. So, let us move on. So, here we have an example that I guess will bring in various aspects together. So, an experiment is run in the lab, and here we in the lab we typically conduct batch experiments, right, and that shows that a toxic compound which we are referring to as trimethyl double death, or which we are referring to, I guess, is TMDD, as TMDD, is removed or degraded by a chemical treatment process. The experiment was conducted in a batch system, which is a beaker in the lab, with a solution that initially contained 10 milligram per liter trimethyl double death. C initial is equal to 10 milligram per liter. Many samples were taken at different times, but all but one were lost due to poor storage conditions. Okay. So, that sample was taken after 30 minutes of reaction and showed a trimethyl double death concentration of 2 milligram per liter, right. How much is it? 2 milligram per liter. So, typically what we try to do is we have concentration here and time here, and let us say we have the initial concentration at time 0, and we try to measure the concentration at different times, and we fit a model so that we can understand what is the order of the reaction and try to predict the behavior of the system in other systems, let us say, right. So, here though looks like we, being the blunderbuss that we are, we lost all these samples. So, we only have the initial sample and this final sample, let us say, right. So, even then you can get some idea about the system, but obviously it is going to be relatively off the mark, right. More the data, more your estimation is going to be nearer to your true rate constant here, right. So, here we have time taken after 30 minutes, this is time in minutes, let us say, and here is what we have, and the concentration was 2 milligram per liter, right. So, what else do we have? We are now asked to calculate the hydraulic retention time. So, hydraulic retention time, to refresh your memory, we said was theta equal to x by u. This is typically used in plug flow reactors. Let us say a river is flowing in this direction, and let us say from Haridwar to Roorkee, let us say this is x, right, and u is the velocity of flow of your fluid. X by u will give you the time that your compound will spend within this system, right, or within the river between Haridwar and Roorkee, right. That is what it will give you an idea about hydraulic retention time. So, again if you multiply that by cross sectional area, that is going to be equal to, I guess in a way, V by Q, right. So, what do we have here? We have, or we are asked to calculate the theta that would be required to achieve an effluent concentration of 1 TMDD from an initial concentration of 10 at steady state in treatment systems that are plug flow and also completely mixed flow. So, again here we have a case where we have a batch reactor, all this data is from batch, and then we are asked to approximate or understand or estimate the behavior in a plug flow system and also in a completely mixed flow reactor now. So, assume that the trimethyl double death is to be removed by a process that can be described as a first order reaction, right, or first order rate equation, and the rate of loss is K1 times the concentration of trimethyl double death, right. So, that is what we have out here. So, now obviously what are the aspects that link what information you can glean from your batch reactor with what you are going to use in your plug flow and your CSTR systems, right. For example, let us say I want to see how this chemical that is being released by the industrial zone in Badrabad is going to affect the population in Roorkee now, right. Let us say if that particular pollutant is being released into the Ganga canal, right, and now how do I do that? Let us say first I need to understand the reactions that are going to occur, let us say within that particular what do we say volume, not volume, control volume. So, I need to first conduct that experiment in the lab to find out what order of the reaction is it and how is it being affected, let us say, right. So, I am going to get the rate constant here, right. From the lab I will be able to get the rate constant, and now I will be able to use that variable to predict what will happen to the compound in the canal, let us say, right. So, that is what we are trying to do out here. So, now let us have our batch system. Let me see if I have a blank slate here. Okay, so blank slate is here, but let us try to calculate what we have. So, from the lab scale, what is the not lab scale for the batch reactor? Again V dC by dt, Q in C in, mass coming in minus Q out C out, mass going out plus volume into rate of formation minus rate of loss. As you know, no flow coming in, no flow going out. So, both of these are equal to 0, let us see, for a batch reactor again, for a batch reactor, right, for a batch reactor. And now what do we have? We are going to end up with dC by dt is equal to rate of formation minus rate of loss. But is trimethyl double death being formed? No, it is not, but it is being lost. And what is the rate of loss? It is given as K1 times concentration of that particular compound, trimethyl double death. So, dC by dt is equal to minus Kc. So, again you can integrate and so on and so forth. So, we will I guess end up with Ct equal to C naught or C initial into e power minus Kt, let us see, right. So, concentration at time t, and what do we have? We know that C initial or C naught, here it is not C out, let me say C at time is equal to 0, right. C at time is equal to 0, we know is 10 milligram per liter, and C at time is equal to 30 minutes is equal to what now? I think it was 2 milligram per liter, right. Typically we need to bother about the units, but here as you can see Ct by Ct equal to at time equal to 0 is equal to e power minus Kt. We see that the terms or the units are cancelling out. So, we do not need to really bother about that. So, 10 or 2 by 10 is equal to e to the power of minus k, which is what we are trying to calculate, into 30, let us see. So, k value, we can get the value of k in minute inverse, let us see, right. So, but obviously typically depending on how you are going to use it in parts A and B, you are going to have to change the units here, right. But again this is the process, and keep in mind that we are just calculating the rate constant. So, let me erase this particular aspect. So, again we will just regurgitate I guess what we have been looking at. Again let us be done with it. So, we have the mass balance equation for a batch system, that is going to be relatively simple, because we have no flow coming in, no flow going out, and no rate of formation of the compound. We know that it is only being lost. So, dC by dt equal to minus Kc, and integrating and so on and so forth. So, looks like we have it to be 0.05 minute inverse, which you can convert into seconds, let us see. So, now the second part of the system was to use this for a batch, not batch, plug flow system, and I guess at steady state. If it was not mentioned, we are assuming steady state, let us see. So, we know from the fundamental mass balance equation u dC by dx is equal to rate of formation minus rate of loss, and at steady state this is 0, x by u is theta, theta is equal to x by u, the hydraulic retention time. So, dC by d theta is equal to rate of formation, which is again 0, minus rate of loss, right. So, dC by d theta is equal to minus k, which you already calculated in part, not part, in the initial cases. Again when we say rate constant, it is a constant for that particular set of temperature, right, for those conditions, pardon me. So, obviously whatever you do in your batch reactor, the rate constant is still going to be the same even in your plug flow system, let us say, right. So, k is going to be a constant and Kc, let us see, right. So, again what do we have? C at theta is equal to C when theta is equal to 0 into e power minus k theta. Again keep in mind it is not changing with time, but the C is changing with distance, because theta is equal to x by u, x is the variable, u is the constant here, right. So, but again when we say dC by d theta, it means that we are changing d theta is equal to 1 by u dx, right. We are concerned with the change with distance, let us see, right, or the average time that your molecule is spending in that system. And what did the question ask us for? I think we have, what do we have? Okay, we need it for a plug flow reactor, and let us say we want a final concentration of 1 milligram per liter if the initial one is 10, fine. So, where were we? Okay, here. So, we know that initial one is 10, final one is 1. So, k is something that you know. So, you can calculate theta in terms of what is it now, because this is minute inverse. So, you can calculate theta in terms of minutes, right. So, that is how you do it. So, even for your other case, what is it? Okay, let us see it calculate for the plug flow reactor. So, dC by d theta will be rate of formation minus rate of loss. Rate of formation is 0 minus K1C. C at theta is equal to, this is not time obviously, at theta naught, that is a typo on my behalf. C at theta is equal to C when theta is equal to 0 into e to the power of minus K theta, right. This is for your plug flow. This is not time, but hydraulic retention time. And so, looks like when you go through the relevant equation, you get 42.9 minutes. So, okay, so now what next? We are in part C, we are going to calculate it for CSTR, or the continuously stirred tank reactor. So, here we are going to use the macroscopic equation. So, dC by dt is equal to mass coming in minus mass going out plus volume into rate of formation minus rate of loss, right. Here if it is at steady state, this is 0. So, what else do we have? So, here 0 is equal to Q into C in minus C out plus volume into rate of formation is 0 minus rate of loss is K times C, right. But C and C out are the same, right. C and C out are the same, right. So, this is the term that we have. And now we have one equation and one unknown, but what is that unknown though? Because we know that C in is 10 and C out, or the final one, is 1 milligram per liter. But my unknown is theta, but if you look at it, we know that theta is equal to V by Q, volume by Q is volume per time, right. So, that is units of time, obviously theta equal to V by Q, right. So, what do we need to do? Let us say we are going to take this term out onto the left hand side. So, V into Kc will be equal to Q into C in minus C out, or C, let us see, right. And theta equal to V by Q. So, I am going to bread this term out here. So, V by Q, which is equal to theta, is equal to C in minus C by Kc, I guess, right. So, that is your hydraulic retention time that we are going to have to calculate. So, for removal of what do we say, the compound from 10 milligram per liter to 1 milligram per liter, in a CSTR, the compound or the water has to spend this much of time. For a plug flow reactor, it has to be 43 minutes, it has to spend 43 minutes. In a CSTR, we are going to have to calculate in this way. So, let us see what we have. So, all this is the same stuff as we discussed earlier or right now, right, at steady state. So, where is this? So, this is what we have out here. If I made any minor errors in the calculation, so you can obviously correct that. So, theta I guess is 168 minutes. So, obviously in a plug flow reactor, for the same removal efficiency 10 to 1, we needed I think 43 minutes, but for a plug for a CSTR, for the same removal from 10 to 1, you need 168 minutes though, right. Again, we can look at the logic why, but I will leave that to you maybe for an exam question, I guess. Let us move on to the other aspects. We have different water quality parameters, as in until now you heard me talking about suspended solids, sometimes about BOD, biochemical oxygen demand, and so on and so forth. Earlier we talked about pathogens or such, right. Let us just try to understand what it is, or what are the general water quality parameters that I am concerned in wastewater treatment and maybe in water treatment too, right. Let us move on without wasting further time. One aspect is dissolved oxygen. So, we know that oxygen is present in the gaseous phase, and if we bubble oxygen into the gaseous aqueous phase or water, it will be dissolved in that, and that we are going to say is oxygen in the aqueous phase or the dissolved oxygen. Why is that required? Let us see that. So, it is called DO. Whenever somebody says DO, this is what they are talking about. It is dissolved molecular oxygen. Why is it that we need to maintain DO in the water? because higher forms of aquatic life, fish, different kinds of fish and such, to give just one example, need DO to live. We need oxygen. Again, different what do we say, types of life require oxygen even in the aquatic environment. If the dissolved oxygen is too low, typically you don't have a thriving ecosystem. You have typically ecologically dead systems. You have pathogens teeming out there and remarkably unhealthy conditions thriving out there. So, how is it that dissolved oxygen is going to be affected or decreased? One is if a DO less stream comes into play, or if I have a lot of organics, C6, not 6, HX. So, this is, let us say, a simple representation of human waste, right. I ate something and I let it out, and then if I let it out into the nature, what is going to happen? It is going to take up oxygen and it is going to go to, let us say, CO2 and H2O or different byproducts, right. So, we are using up the dissolved oxygen. This is in the aqueous phase, dissolved oxygen, and thus we are creating anaerobic conditions or no oxygen conditions in our environment, which is unhealthy. That is something to keep in mind. What are the different water pollutants? So, thus if I am concerned about DO, I am concerned about oxygen demanding material, right. And then nutrients, we looked at this, I believe, nitrogen and phosphorus typically, and then pathogens, disease or organisms capable of causing disease to humans or such. Suspended solids, right, we will look at this in detail, but for today I will try to touch upon this particular aspect out here. So, oxygen demanding material, what do we typically have? I have biochemical oxygen demand, a way of approximating the amount of oxygen demanding material, but this is relatively slow. So, another way which is relatively faster is chemical oxygen demand, again a way of approximating the oxygen demanding material. And what is the oxygen demanding material? Typically are waste or the industrial waste which are reduced compounds. You see it is relatively reduced out here, we have the H out here, right, and if it is completely oxidized, it would go to carbon dioxide. Here it is relatively oxidized, here relatively reduced, let us see. So, how will they go from here to here? They will need oxygen to go from here to here, right, and that is why these compounds we are calling them as oxygen demanding material, and we are using variables such as BOD or COD to try to approximate this oxygen demanding material. The difference between these two, as you see, biochemical oxygen demand and only chemical oxygen demand, let us see, right. So, let us go forth and look at what it is that we mean by when we say BOD. So, please pay some attention. It is the amount of oxygen consumed by microorganisms as they consume the biodegradable matter. So, three aspects: oxygen consumption, so thus oxygen demand, and that which is consumed by microorganisms as they try to consume or degrade biodegradable organic matter, typically biodegradable organic matter. That is the definition of BOD, let us see, right. Let us look at what we have out here. So, we have the microorganism out here and we have the glucose or such out here, which is the food for the relevant microorganisms, right. Our waste, let us say different forms, here we have C6H12O6 though, is the food for the microorganisms, but what do they need to be able to make use of this particular food for them and our waste? They need oxygen, right, they need the dissolved oxygen. So, that is what they have out here. So, BOD requires microorganisms that consume oxygen in the process of degrading organic matter, right. So, our waste is their food, which is typically called substrate in general, let us see, their food meaning microorganisms food. So, definition of COD, it is the amount of dichromate, we will see why dichromate, which is consumed in the oxidation of inorganic and usually certainly organic matter. So, here we are trying to get at understanding the oxygen demand, but chemical oxygen demand, and I want the time taken for the test to be less. So, when we are looking at microbes, the time that it takes is relatively higher, let us see. So, let us say test that takes 5 days, I do not have the time and I need the results or need to be able to understand the system relatively earlier, let us say, right. I cannot wait for 5 days to understand the performance of the plant or such. So, I conduct the COD test. So, that is why instead of the microbes using oxygen, I try to indirectly measure the amount of oxygen. How? Oxygen is an electron acceptor. So, rather than electron acceptor, I am going to use dichromate, which is a relatively strong oxidizing agent, meaning a relatively strong electron acceptor, let us say, and then I will look at the electron equivalents to get it in terms of oxygen, right. So, it is the amount of dichromate needed to oxidize, right. So, the inorganic and organic matter, we are not saying biodegradable organic matter, we are saying inorganic and organic matter. So, that is something to keep in mind. So, COD, let us say it is just the dichromate out here and such, and we are going to give it in terms of oxygen equivalents, let us say, right, but it is not actually a reaction occurring between oxygen and the relevant compound of interest, right, but we are just trying to understand if all these compounds need or eat up here, right, oxygen to be oxidized, how much will the oxygen demand be, that is chemical oxygen demand. So, it is a chemical oxidation, there are no microorganisms here, right, this is not a microorganism, just the representation of the compound of concern. How do we look at the BOD and such, or how do we measure it? There are simple ways, but I am out of time. So, thanking you for your patience, I will end today's session.